1. Task Introduction. Understand the basic components of a CNC lathe. Master the fundamental operations of CNC lathe. Gain a clear understanding of the sections involved in the CNC system startup circuit, and be able to correctly design, install, and debug the CNC system startup circuit. Familiarize yourself with the model types of the CNC lathe servo drive units. Clearly understand the meaning, purpose, and functions of each interface in the servo driver, and ultimately be capable of properly designing, installing, and debugging the circuits for the drive unit. 2. Learning objectives. Knowledge objectives. Understand the basic components of a CNC lathe. Clearly grasp the sections involved in the CNC system startup circuit and the corresponding implementation measures. Be able to correctly explain the meanings of the interfaces of the servo drive unit. Skill objectives. Be able to correctly design, connect, and debug the CNC system startup circuit. Be able to correctly explain the meanings of the interfaces of the servo drive unit. Be capable of properly designing, connecting, and debugging the circuits for the servo drive unit. Caliber objectives. Establish correct outlooks on life and values. Develop a spirit of craftsmanship and foster a work ethic grounded in rigor and standardization. Build strong safety awareness to ensure the safety of personnel and equipment. 3. Guiding questions. 1. What are the basic components of a CNC lathe? The basic components of a CNC lathe mainly include the CNC system, servo drive unit, spindle drive unit, programmable logic controller, PLC, input-output unit, feedback unit, and the machine tool body. 2. What are the basic sections involved in the CNC lathe startup circuit? The CNC lathe startup circuit consists of sections such as voltage transformation, AC to DC conversion, CNC system start-stop control, and DC voltage input. 3. What types of interfaces are typically included in a servo drive unit? A servo drive unit typically includes the following: high voltage input and output, system command input, feedback from the detection unit, control power supply, enable control, and a communication interface. 4. Knowledge description. 1. Structure of a CNC lathe. As shown in the diagram, a CNC lathe consists of the following components: control panel, CNC system, electronic hand wheel, switching power supply, emergency stop switch, coolant tank, leveling feet, LED work light, work status indicator, machine side door, spindle chuck, and tool compartment. 2. Basic operations of the CNC lathe. 1. Powering on. Typically, the machine is powered on first, followed by the control system. In some designs, the two are interlocked. If the machine is not powered on, no information will be displayed on the CRT monitor screen. First, turn on the main power switch. Then press the start button to power on the system. Press the stop button to power off the system. 2. Returning to reference point. For machines with an incremental control system, this step must be performed first to establish the movement standards for each machine axis. In reference return mode, select the desired axis. Then press the positive direction key to move the machine back to its reference point. 3. Program editing and input. If the input program needs modification, editing operations are required. Switch the mode selector to the edit position and use the editing keys to add, delete, or modify the program. 4. Machine lock. Press the machine lock button. When executing a machining program with the machine locked, the machine itself will not move. Only the tool position changes are displayed. This function is used for program verification. 5. Manual operation. Select the manual mode as shown in the diagram. Choose positive X or negative X, positive Z or negative Z to move the axis. If the control panel includes axis and direction selection, first select the axis, then press the positive or negative direction key to move the machine. During movement, adjust the feed rate override knob to observe changes in movement speed. 6. Handwheel feed. Select the handwheel mode. Choose the X or Z axis. Then select a feed rate scale such as X1, X10, or X100. Rotate the pulse generator to move the machine. 7. MDI operation. In MDI manual data input mode, write a short program for feed or spindle operation. Then press the cycle start button and observe the movement of the machine axis or the operation of the spindle. 8. Automatic program execution. First, press the program key to enter the program set. In the program page set, use the page up, page down, up arrow, and down arrow keys to move the cursor and select the desired program. Or use the search soft key to find the program to be executed. The selected program line will be highlighted with a green background, as shown in the figure. After programming is complete, mount the workpiece, perform alignment, and set the tool using manual incremental movement, continuous movement, or the electronic hand wheel. Align the tool setting point with the program starting point and correctly set the tool reference position. Program simulation. In automatic mode, lock the machine, access the graphical interface, and press the graphic setting soft key. Adjust the graphic display position by modifying coordinate offsets. Press the cycle star button and then the trajectory display soft key to enter the trajectory display page and view the current program's execution path. If the graphic position is not appropriate, use the center, zoom in, and zoom out keys to adjust the display. Running the program. Disable the machine lock button. Press the cycle start button to execute the program. During machining, the feed speed can be adjusted using the feed rate override switch. During machining, pressing the feed roll button will pause the feed movement, allowing you to inspect the machining or perform manual measurements. Press the cycle start button again to resume machining. 9. Operation display. Use various CRT screens to display the position of the work table or tool, as well as the status of the program and machine, enabling operators to monitor the machining process. 3. CNC system startup circuit design. 1. Circuit design for high voltage transformation and AC to DC conversion. The CNC system startup circuit supplies the required 24-volt DC power to the CNC system. This circuit mainly accomplishes the following tasks: transforming the incoming 380-volt AC high voltage electricity through protection, voltage transformation, and conversion to a stable 24-volt DC output, and then delivering the 24-volt DC to the CNC system. It involves 3 main stages. 1. Step-down process of 380-volt AC. As shown in the diagram, the externally supplied high-voltage AC, 3-phase 380 volts, first passes through the circuit breaker QF4 for protection, then through a transformer that steps down the voltage to 220-volt AC. 2. Conversion of 220-volt AC to 24-volt DC. As illustrated, the 24-volt DC voltage is mainly produced by a switching power supply. The 220-volt AC output from the transformer passes through circuit breaker QF5 for protection, then through the key switch SA0, entering the switching power supply VC1. The output voltage from VC1 is 24-volt DC. 3. Control of supplying 24-volt DC to the CNC system. When the start button is pressed, the system is powered on. When the stop button is pressed, the system is powered off. Thus, the startup circuit must be controlled by the start and stop buttons. As shown in the diagram, pressing the start button, SB4, energizes the coil of the intermediate relay KA1. Pressing the stop button, SB3 de-energizes the KA1 coil. To maintain continuous power supply, a self-locking control method is used. Finally, using the contacts of KA1, the 24-volt DC is delivered into the CNC system. 4. Servo drive unit and its circuit. 1. Servo drive model and naming. As shown in the diagram, the servo drives include the CD pulse series and the FD bus series. The CNC lathe uses the FD bus series, operating at AC 220 volts, with an output current of AC 220 volts 2 amps. It is a third-generation product that uses RS485 interface communication, and the software version number is 000. 2. Servo drive interfaces and their descriptions. 1. Power cable interface X2. As shown in the diagram, X2 is the power cable interface. L1C and L2C are control power supply interfaces, providing power to the drive unit circuit board. L1 and L2 are the high voltage power input terminals for the drive. When the motor is a low power motor with power less than 1 kilowatt, a single phase power supply is used. DC plus and DC minus are the DC bus terminals. RB1, RB2, and RB minus are the braking resistor terminals. When using an internal braking resistor, RB1 and RB2 should be short-circuited. When using an external braking resistor, RB1 and RB minus should be short-circuited. U, V, and W are the output terminal for the motor. 2. External input-output interface X4. The X4 interface is used for external input and output connections, consisting of 36 terminals, each with its specific function. These terminals are used to receive external input signals and to perform control in position mode, speed mode, and torque mode. It also includes encoder output terminals, which send the feedback signals from the encoder back to the CNC system. As shown in the diagram, pins 27, 29, 31, and 33 are command pulse input terminals. These support pulse plus direction, CW or CCW clockwise or counterclockwise pulse, and AB phase pulse control modes. Pulse plus direction. The command signal is a pulse, and the direction is indicated by a high or a low voltage level. A high level indicates forward rotation, while a low level indicates reverse rotation. CW or CCW pulse. During forward rotation, the pulse signal is output on the command terminal, while the direction terminal holds a steady voltage. For reverse rotation, the command terminal outputs a steady voltage, while the direction terminal outputs a pulse. AB phase pulse. Both command and direction signals are output as pulses, with a phase lead or lag between them, which determines the forward or reverse rotation of the motor. Pins 26, 28, 30, 32, 34, and 36 are used for encoder output signals. Pins 26 and 28 output the Z phase 0 pulse signal, used as a 1 rotation reference mark. Pins 30 and 32 are for the B phase signal. Pins 34 and 36 are for the A phase signal. These signals are used to detect the motor rotation speed and determine the direction of rotation. Pins 4, 6, 8, 10, 12, 14, and 16 are digital input terminals, typically used to receive signals such as drive enable, fault reset, home position setting, and positive or negative limit switches. 3. Encoder input interface X5. The encoder input adopts serial input, received through the SD and /SD ports. Pins 1 and 2 output positive 5 volts and 0 volts voltage signals to power the encoder. The clock signal ensures that serial output data is transmitted sequentially according to the clock pulses. 4. Communication bus interface X10. The X10 port is the communication bus interface. The left side port supports the EtherCAT bus, suitable for FD series servo drives that use Ethernet-based communication. The middle interface is for the CAN open bus, supporting FD series servo drives with CAN open transmission. The right side interface is for the RS485 bus, specifically for FD series servo drives using RS485 based communication. The CNC lathe uses the FD423 LA000 servo drive. Therefore, it uses the right side RS485 bus interface. In this interface, plus 5V and GND are the power supply terminals. TX plus and TX minus are the data transmission terminals. RD plus and RD minus are the data reception terminals. 5. Communication settings DIP switches SW1 to SW8. The communication ID of the FD3 servo drive can be set using the DIP switches on the panel. Changes to the DIP switch settings take effect after the drive is restarted. When SW1 to SW8 are all set to off, the drive reads the communication ID stored in the EEPROM. Users can also modify the device station number via communication settings. 3. Servo drive circuit design. When designing the servo drive circuit, the following elements are included. System command control circuit. The X4 port of the servo drive connects to the CNC system to output system control signals. Servo high voltage input circuit. Since the motor used in this servo drive is relatively low power, it uses a 220 volt AC power supply, which is input through the L1 and L2 terminals. During the high voltage transmission process, a circuit breaker is connected to provide protection against short circuits, overloads, and undervoltage. Then the power passes through an electromagnetic contactor and a noise filter, which eliminates noise and ensures the stability of the input signal. Contactor control circuit. This circuit is controlled by the system startup signal. When a start button is pressed, the startup relay is energized, and the relay contacts then control the closing of the servo drive's electromagnetic contactor. Encoder feedback. The encoder feedback signal comes from the built-in encoder located at the rear end of the motor and is input to the X5 port of the drive as a pulse signal. To ensure signal accuracy, there must be no interruptions or disconnections during the input process. High voltage output circuit. This circuit transmits the inverted signal generated by the servo drive to the motor. The signal is output from a U, V, and W terminals of the X2 power cable interface and connected to the corresponding terminals of the motor. Controlled power supply circuit. This is the power supply for the drive's internal circuit boards. This drive uses a 200 to 240 volt controlled power supply, which is input through the L1C and L2C terminals of the X2 power cable interface.